And sorry for that bit of music silence and then delay. Just found out I had a battery in the microphone that was out. So we had to do an immediate upgrade, I think is the phrase we'll use there. And of all things, today is sunshine, beautiful weather, and the Amgen was yesterday. Rain, not as nice as today. No justice, I think. I just collected the assignment from 3-7, and so that is part of what we talked about yesterday, and we go into Chapter 4 today. So I have some mixed feelings about Chapter 4. Before we do that, let's take time to at least, Ernie, I know we were listening to Jim Morrison and the Doors and the selection that we interrupted briefly. Light my fire, and the reason for that is it is almost 64 degrees in this room today. So if you're feeling chilly, cold, just think warm thoughts. And maybe if we think warm thoughts, the temperature will go up, right? Equations and solutions. That's what 4.1 is about. It's a very brief section. It seems to me, looking at what we've been doing, that it might be such that we could do 4.1 and 4.2 today. I don't know. We're going to see. So I had originally scheduled 4.1 for today and 4.2 for tomorrow, but looking at the material, there's not a whole lot that can be said in terms of how to solve some of these first equations. So let me get some things going here. The objective, first one, is a rather interesting objective, one that I think is rather critical as we go to the document cam now, is to differentiate. That means find or determine the difference, be able to tell the difference between an expression and an equation. So let's come off there for a moment. There is a similar concern that we had out of Math 10, and that was making sure we understood what a factor was. And as we look in Math 20, I'd say there are two major problems that we have to deal with. Being able to distinguish between a term and a factor, an expression, and an equation. Those sort of go hand in hand. So as I go to the board in this, Ernie, and we look at what we have, if I have 3x plus 5, we're wanting to recognize that as an expression. But not only that, we're trying to make a distinction between an expression like this and an expression that I would write this way, where the 3x is a factor. So here the 3x is a factor, here it's a term. So we have a term here and a factor here. Now that's going to be a very important distinction we make when we solve equations. So for example, if I have 3x plus 5 is equal to 20, that becomes an equation because we have an equal sign. This was an expression. What's the distinguishing difference? The equal sign. Yes, question?
On the bottom, on the 3x, is that a factor now? 3x?
This 3x is a term.
It's still a term.
A term of the left side of the equation. If I factor 3x out of what was, in essence, a binomial with the greatest common factor, then the 3x sits there as a factor. Now, when we solve equations, and I'm looking at this one, now you can, I hope, just look at it and say 5 works. If x is 5, the left side gives you 20. But how do we approach that in terms of solving it algebraically? Now, by that I mean you aren't just looking. You can think of adding negative 5 to both sides. So if I trade it in, and that's what we've done before. We haven't talked about it so much. We say there's an equivalent equation. And the equivalent equation that we talked about earlier was doing this. But in essence, you subtracted 5 from both sides, or you added. I could have treated that. Let me get an eraser and sort of disappear momentarily. You can think of saying that I simply added negative 5 to both sides. Now, how do I get a term from one side to the other? How do I get rid of a term? And the answer is adding its inverse or subtracting. So if I want to get rid of a term, I didn't like that term on this side. I wanted x by itself. So I got rid of that term by adding its inverse. Now this gives me 3x equals 15, correct? And this is where people get burned, because they'd like to get rid of that 3. But 3 is no longer a what? 3 is no longer a term like this was. 3 is a factor of that term. So 3 isn't a term like the 5 was. It is a factor of this left side. How do I get rid of factors? Either dividing by the factor or multiplying by its inverse. So you can think of saying, I'm going to multiply the left side by 1 over 3 and multiply the right side by 1 over 3. And if I do that, I get the x equals the 5. Kim?
Negative 5? No?
Well, I had 20 plus negative 5 up here. That gave me a positive 15, correct? And if I divide 3 into 15, I'll just get 5. But again, the point being, I remove a factor by a division process. I remove a term by a subtraction process. And that's what 4.1, 4.2, and 4.3 are about. So this distinction between an equation, so this becomes the equation here, and this becomes an expression, because the expression didn't have an equal sign. So you have to be able to distinguish that. And that, again, is pretty easy if you remember equations have an equal sign in them. So that first objective is one that's pretty easy, I think, to do. Now, the second objective in this set is to see if a number is a solution, as we go to the document cam now, is a solution for an equation. As we come off there, the question is, where are you getting the number? So what I could do, if I wanted to check that objective, I could say, check to see, or check if x equals 5 is a solution of the equation, in which I would have my equation 3x plus 5 equals 20. Now how do I check that? Substitution. I will simply replace the x by the 5. And so I ask, is 3, and sometimes I like to put parentheses here to indicate the multiplication, is this equal to 20? If it is, and let's just slide over a little bit, Ernie, and I'll need a little bit of spot. Thank you. If it is, then I have a solution. So it's still a question mark here, and 20 is equal to 20, so we say what? 5 is a solution of the equation. Now, nobody's told you at this point how to get that 5. You could simply look at this and guess the number and show that it works. The equations get worse than this, so that look and see kind of approach isn't going to be what we get by with all the time. But is there any question up to that point? Sandra?
So this one over here, is there any other way to do it besides?
What I did over here, sliding over just a little bit, how I did this one?
Yeah, is there another way to do it besides the fraction?
You could have divided both sides by 3. I could have just taken the 3x and the 15, and I could have, as I slide back over here, do it this way rather than multiplying by 1/3. I could have just done this and then said x equals 5. And that, when I'm doing problems, tends to be what I do more often. But at the same time, I'm wanting you to understand that when I multiplied by the 1/3 on both sides here, that was what? That was a property. Multiplying by the inverse, the reciprocal of the factor. So if I want to get rid of the factor, multiply by its reciprocal. Part of that neat language. Okay?
So I should probably do it that way.
Well, you should do both. This is in practice when you want to get things done in a hurry. This is good form. So you practice form, and then you sometimes do it a little bit faster. Any other questions there? Okay. Those are the two principal objectives in this set, and the kinds of problems that are there in some ways don't make me feel very excited. Not that excitement is necessarily what we want, but in mathematics it's nice to get excited once in a while. Here is a question on page 239 to see if 3 is a solution of this equation. So how are you going to do it? Substitute 3 in. Does it work? Yes, it's pretty straightforward. I mean, it's not something to get very excited about. So the question is, do things get any better than that? And I'm just going to write a problem on the board rather than doing one from the book. But I'm going to write something, and then you have to make a judgment of what is the best to do. So let me go to the board now and say that I had 3x plus 5 minus x equals 2x. Bad choice. Just a moment. I'm going to make this 8x. That's an easy change you can make. And so, and here I'm going to have a minus 10. Now, what might you want to do with this problem? In fact, I think I'm going to see if I want to do something else there. Just a minute. I have I'll leave that. I could ask you the following. Is 3 a solution to that equation? Now, if you were to, question, is 3 a solution? Now, you could do what with this equation just as written? Substitute right now. Agreed? What might make more sense? Any idea? You might do something different than substitute immediately? Okay, not quite that far. I could get x by itself. That would be algebraic, but I'm just wanting to substitute and check. Would it make some sense to combine these two terms? So you have 8x. This is Isaac's minus 1x to the first. But that means we have a 7x plus 5. And I want to know, is that equal to 2x minus 10? Okay. Now, in terms of what I've done there, okay, I want to know, is 3 a solution? And it's easier to do here than it is where? In the original form. You don't have to do this simplification, but it's not a bad idea. Now, if I'm going to carry it further, and this gets back to James's suggestion, and it's technically not in this first part, but I don't like the 5 there. I would subtract 5 from both sides. So my next step would be 7x is equal to 2x, and then I'm subtracting 5 from both sides. I dislike that step in some ways because you start doing that and it slows you down. So I would have much preferred just to say 7x is 2x minus 15. Okay, then what would I do? Well, I'd like x's together in one side. So the goal I would have is to subtract 2x from each side So I'm going to think of subtracting a 2x from each side, and this is going to give me a 5x. This is going to give me a negative 15. And then I'd like to do what? Get rid of the 5 here because it's a factor. So this I end up doing, and I actually get x is equal to negative 3. So was 3 a solution? No, it didn't work. But negative 3 would have. So what you were supposed to do, rather than solve, this goes under that infamous phrase, solve for x. Here, to check a solution, all you were expected to do is 8 times 3 plus 5 minus the 3. Is that equal to 2 times 3 minus 10? Well, here we have 24, 29, minus 3, so that's 26. And I want to know, is that equal to 6 minus 10, which is a negative 4? And the answer is no, so not a solution. Michael?
So that's the process to get x by itself?
This would be the process, and the point being, this is going to be split into 2 sets of problems. One where you don't have to do anything with division. Everything's with addition and subtraction. And then we do a set with division. Trying to piece it together because this is juggling 3 things at a time. Okay, you're going to subtract, you're going to divide, you're going to check the solution. And if you aren't careful, they all go on the ground. So, if I come back to center, again, thinking of what our goal here is, in the problem that we just looked at, it's something like this one down here on number, I guess it's example 4 in 239. Here's my problem. Negative 3n plus 8 equals 2n minus 17. And the argument is to try to substitute directly. I was going to see if there's another problem a little bit better than that. Okay. Not anything as bad as what I was looking at. In fact, everything in this set is nothing but just plug in and check. As an engineering student, we had a phrase for that. Plug and chug. Plug in a value and chug through the solution. Procedure, that's about all there is this, and we need to go further than that. But the procedure at the top of 239. Replace the variable with the number. What's another phrase for replace the variable? Substitute. Then simplify both sides and see if you get the same number on each side. Okay, enough said with that. Anything else that we need to look at here? I was just looking at a harder problem, and let's see what we have here. This is a problem, at least in terms of what you might ask, is there a better way? Now here's the problem. This is on page 240. The book doesn't flatten out as well as I'd like, but it's the example 6, and you want to know whether or not negative 5 is a solution. Now, you could simply substitute in the way it's there, or you could do what? Simplify the right side. Otherwise, if you use the distributive property there, on the right side, and I think of what I have there, this would be a negative 12a and a negative 28. Now, what is shown here is just a pure substitution. And there are times when it works out rather nicely, because if I put negative 5 right there for the a, this just becomes 2 times 1. That doesn't get any nicer. So you don't gain anything by using the distributive property. On this part, where you have a negative 5, this doesn't really end up lending itself. That's negative 15 plus 7, which is a negative 8. And so that doesn't get any better just by substitution there. I would be inclined to try to simplify first. But as you can see as we come off there, in this particular solution, This is where the substitution's been made. Let me get that up a little bit higher. There are the steps for people who are watching it and don't have a book with them. You can see how the substitution was made, and you simply carry through these steps. Here was your 2 times 1. That was the easy part. Over here was your negative 8 I was talking about. And then you have a negative 32. This is where you have to be careful because you'd have a minus and a minus. So that makes it a positive, and it does work through. So yes, you can change or you can substitute into complicated expressions. I don't think we want to carry that to an extreme. I think about 10 of those, and you get the idea without hitting you over the head with the 2x4. So let's move on. Now, I said the next couple sections, we expect to see 2 things done. One is the addition subtraction, that's 4, 2. The idea, if we want to get rid of a term, either add its inverse or subtract. Okay, and the objective is still to determine whether a given equation is, I guess we have a new one here, is linear. Okay, I want to talk about that for a moment. But before we do that, let's come off there. And then I want to look at section 4.2. This section 4.3, I should say. This section goes for quite a ways. Here's what I was mentioning. We've combined these already, but let me get this flattened out, Ernie, again, if I can. Without having a hard cover, this is sometimes hard to do. But this is section 4.3, and that's the multiplication principle. So I'm going to come off there for a moment. I'm going to go back to the board. And what I'm trying to share is that if I give you this kind of problem, I hope, in fact, 13 is a 2-digit number, and I wasn't meaning to make it that complicated. But I hope you can see the 13. It's a no-brainer. Agreed? Straightforward? Now, this is an addition property. Add 4 to both sides. The left side becomes x plus 0. The right side becomes 13. And by the identity property of addition, this becomes x. And so you just have x equals 13. Agreed? Straightforward? Now, there's a whole set of problems like this. We can make them a little more complicated, and I'll share that in a moment. But now here's the next problem. Now, to get x by itself here, I'm going to divide by the 3 again. We talked about earlier, same problem. Now, those are 2 separate approaches. Add the inverse to both sides, or divide both sides, which is the multiplicative inverse. And this comes out with a statement like this. If A is equal to B, then A plus C is equal to B plus C. Now, that is a property of equality. We talked about properties of the real numbers, correct? Ernie, slide over so I can be on this side a little bit, if you wouldn't mind. Just slide over the other. Just move, pan over. Okay, now, this is a property of equality, as opposed to a property of numbers. We said, if A equals B, B equals A. That's a commutative property about 2 numbers. Okay. Now, relative to equality, which isn't about numbers in the same sense as the 11 properties, if A is equal to B and I add the same number to both sides, I'm supposed to still have an equality. So this is called the well-defined property of equality with respect to addition. You can add the thing, both sides, same thing to both sides, and you still have something equal. In the same way, we can say that if you divide both sides by C, you'll still have equality with one little restriction. you can't divide by 0. C not equal to 0. That's my restriction. Okay. A property of equality says that you can add the same thing to both sides, still equal, divide both sides by the same thing, and still equal, as long as you didn't divide by 0. That's what these two sections are about. Okay? Well-defined property of what it means to be equal with respect to addition and multiplication, because I'm really multiplying by 1 over c. Any question? Because that's an important concept in algebra that we continually come back to. It's interesting as I come back center that this process is going to be illustrated by a scale. So the argument here is I have x plus 7. In fact, if we come off there for just a moment, and I think this is carrying graphics a bit extreme, but you let me know if it works. Here's my original scale. That's what the equal sign means. Now this is technically called a beam balance. And I don't know if it makes any sense to people in LED readouts. Have any of you ever tried to weigh anything with these kinds of scales? Yeah. Okay. There are things that we would do with this. I will take that question back. However, in the usual process, we'd have an LED readout. But if something balances here, and I put a little bit more in this pan, what's going to happen? This pan's going to dip down, correct? So if I added a 4 to this, then this would dip down. If I added a 4 to this, then it would balance back up. That's the idea. So as I come off there, the bad part of this is you should add a negative 7. And how do you add a negative weight? So why we're going to add a 4 here, I mean, this seems like pushing the point a bit much because there's no justification for adding a 4 to the scale at this point. Now, if I add a 4 to both sides, things balance out again. It was a bad choice because now I have x plus 11 equals 13. That didn't gain me anything. But that's the idea. So instead of adding a 4, what would you really like to add to both sides? A negative 7, correct? So originally, if you had x plus 7 equaled 9, if you just added a negative 7 to both sides, you'd have x equals 2. Done. Any question there? So we come off the scales. Yes, Michael.
How are they balanced if they're different numbers?
As long as the original balance was there, and we added 4 to both sides, correct? Okay. It's still going to be balanced. It was not wise to add 4 because you'd like x by itself. So what we should have said, well, if I pull 7 off the left side, then it's like a teeter-totter. That side's going to go up. But then if I take a 7 off the other side, it'll be balanced again. Right? So as I say, well-intended in terms of the illustration, it just doesn't make any sense for that problem why you'd add 4. I might be guilty of the same thing if I were writing the book. Let's look at the rule on page 244. Going to the document can, Ernie. We have the same amount can be added or subtracted from both sides without affecting its solution, meaning things are still equal. You're going to get the same solution you had before. So as I come off there, and then what I'm going to do, Ernie, is go back to the board over here. If I have an equation like I did here, it has a solution. Now I'm going to get what's called an equivalent equation by adding 4 to both sides. So that's an equivalent equation. By equivalent, I mean it has the same solution. So whatever worked here still works here. This is another equivalent equation. This is about as simple an equation as you can get because you can eyeball its solution. 13 works. You're done. Now what we sometimes do, and you need to be aware of this, we say the solution set is the set containing 13. And those little braces that we've been working with, in this case, designate a collection of numbers, something that makes it a true statement. For right now, we're only getting one solution. That's it. Soon, we will get two solutions, sometimes three. But this is referred to as a solution set. And the reason I want you to be aware that that's called a set, if you end up later on going into statistics, we work with the idea. In fact, this morning we were talking about problems with rolling dice. And we're talking about the set of outcomes. And I need to have you understand what a set means. Okay? So nothing particularly new there in concept, but an equivalent equation simply means you have the same solution that you had before. Coming back, center. Procedure. To use the addition-subtraction principle, note, to clear a term. Translation, wipe it out. Get rid of it. So to get rid of a term, to make it disappear from one side, then use the additive inverse. You add it to both sides. You would translate that into what? Rather than add the inverse, subtract the same thing from both sides. There was a time in algebra, and I'm going to come up to the board here again, Ernie, as we bounce back and forth, where my next step from here would have been this. Rather than adding the 4 down here, write it up in the same line. Does the same thing. Okay, but this is mathematically better than what's being done here. But from a practical experience, I would go from here down to here in a heartbeat without doing anything in between. Again, you've got to make that balance. Be a little bit careful what you don't do as intermediate steps right now. The intermediate steps can be very critical to you. Any question in that? Okay. There's a statement that's made by the author in the text I have about whether you show that 0 or not. So if I go back, Ernie, I keep bouncing back and forth, but if I come to here, the question is, do you need to show this statement of x plus 0? No. Does it help? Maybe yes, if you're trying to remember what the identity is for addition. My concern is things you skip, you tend not to remember. Things that you write out right now will help stay in your head. The things you write out in intermediate steps are going to slow you down. So there's got to be that balance. You have to find a balance between, do you understand why you're doing it, and can you keep doing it correctly, and then let go of the training wheels. Remember learning to ride a bike, since bike racing's been the big thing the last 48 hours? Somebody holds on to you for a while, or you get training wheels. The way I did, they gave me a bike, and there was a fence, so I pushed myself off from the fence and ride a little bit, and then fall into the fence, push yourself off, ride a little bit further. But it was my version of training wheels at that time. Until finally, you can do what? Ride without the training wheels. But you take some pretty good crashes until you do that. Okay? That's a little bit of what we're talking about here. Again, without belaboring it, making it go too far. What happens if things are a little more complicated, and that's where we hit this next problem on 247. So we have, let's see what the equation is. I need to get down a little bit further. There it is, and the phrase. Solve and check. Now, what does check mean again? Substitute to see if your number works. Plug in your value when you're done. Now, for the most part, as we come off there, practical point of view, when I'm doing these kind of equations, I hardly ever check. I know how to check if I need to. So again, how many times should you check the solution to make sure you'll not forget how to check? That's a balance. Whether it's 10 or 100, I don't know. And that's the dilemma. Okay? You do something once, it's not enough. I guarantee you that. Doing it 100 times is probably too much. Somewhere between 1 and 100 to where you don't forget it. That's the concern. So in this problem, let's come back to the statement. I have 7x minus 9 equals 6x minus 11. And your goal is to get x by itself on one side. So again, looking at this equation, I want to get an equivalent equation with x by itself on one side. That means I'd like to get rid of this 9, correct? How can I get rid of that 9? Add 9 to both sides, correct? Then how can I get this 6x over on the left side where I want it? Add negative 6x to both sides or subtract 6x from both sides. And when you do that, life gets good. Because all these problems tend to be rigged so that when you do them, all you have left is x. It's the next section you get a 3x or a 2x or something like that. So when you write these problems, everything's supposed to come out nicely. X by itself. Well, here's where negative 6x was added to both sides. So what I'm going to do, Ernie, is leave this up on the screen. And let's go to over here. And in what I'm wanting to do, we're going to write the equation, then we're going to cut to the side. So I have 7x minus 9. And that's equal to 6x minus 11. Now, I'd like to get rid of the 9. It's a term, so I add its inverse. I like this better. If you aren't going to do it in your head and you want to write it out, this is adding the same thing to both sides. And right now, maybe for a few problems, not a bad idea to say 7x plus 0 equals 6x minus 2. And of course, when you add 0, you get what? What you started with. So this is 7x equals 6x minus 2. And now I didn't want the x on the right side, so I will do what? Add its inverse to both sides. At about this point, you're bound and determined to make some silly mistake. I traded the minus 2 for plus a negative 2. I traded in the subtraction for the addition of its inverse. These two parts go out, of course. Here I have x. On the right side, I'm going to have 0 plus negative 2. And so x is equal to what? Negative 2. Folks, that is a lot of work. Let me show you what I do in practice. Michael first.
Was it just coincidence that when you added the inverse to the negative 11, that you got the negative 2, that was the solution?
The question is, because I'm not sure it can be heard in the tape, the question is it a coincidence that when I ended up with this negative 2 on the right side, that that's what x was going to be? It's not a coincidence in these problems because they're rigged so that you'll get x on the left side. So the only thing you're doing is adding and subtracting. When I no longer get x on the left side, then no. So for example, if this had been instead of 7x, I had here an 8x instead of 7. Everything else the same. This would have been 2x equals minus 2, and then you'd have divided both sides by 2 to get minus 1. as your solution. So it's a coincidence by design, by manipulation, so that you don't have to do something more than add or subtract. Because the minute I allow for a 2x here, then I've got to talk about division on both sides. So to that extent, not a coincidence, but not something I want you to generalize that that's always going to happen. Okay? Now, how would I do that in practice? I'd look at this and I'd say, gee, I'm going to take 6x from both sides. So that gives me x. I'm going to add 9 to both sides. That's -2. I'm done. I would do those 2 steps in my head. Now, shortly, the problems get complex enough you can't do that. For right now, yes, you can. So again, and I'm going to need some feedback from you, because I don't really have a sense at the moment of how much repetition is necessary for this, for you to feel like you've got it nailed down. And you've got to let me know if this is getting to be a problem for you. Okay, because you've got to find a point at which you understand 1 and part 2 can do the problems quickly and accurately. Michael?
I don't think that just computer work is enough to actually get it.
I think this is where you really got to write some things down. Because you're going to be tempted to play the game I did just up here and not write a single thing down. And I think that's dangerous at this point. You have to have something physically that you're doing to help create that memory. That's interesting. Sounds like something for scrapbooking. Create memories. We'll get together and create memories today. We'll do photo albums, or it's the kind of thing that James and Shannon and Kyle and I went down and we created a memory. Took pictures. You have a picture of it. Reminds you of what you saw. Because that silly race went by so fast that, 1 second, 15 seconds later, everybody's gone. Okay, so you've been there. We waited an hour for 15 seconds. Okay. Now, they came around again, but still, the memories are hard to keep in your head unless it was something that just really, sometimes the things that we don't want to remember are the ones that get remembered. How do you create a memory of what goes through here? And that's where we talk about repetition, doing it over and over and over, so it nearly becomes a subconscious activity. Now, you do it in a lot of other arenas. You do it in driving, when you learn to drive. You learn to shift the gears. You learn to look in the mirrors. All so you can pass the driving test and get a license, assuming you're driving legally. And you didn't object to it. You did it until it happened. I mean, I can imagine that you may have sat in a car before your license trying to go through a 4 or 5 gear pattern on a stick shift so you didn't make noise doing it out in the street and embarrass yourself. Okay? You learned how to clutch and shift gears before you ever went out and tried it, until it finally just became automatic. And then you bought an automatic, so you didn't have to do it any longer. But this process, you somehow have to do the same thing. And so let's cut back to the document cam. How much of those you need to show? Enough so you know what you're doing. I think that's the critical issue. You have to make a choice, and I would really love some feedback. How many problems do you have to do? And if you're doing it on the computer, here's the danger. You do 30 problems in the computer, you never document, never show anything, and on the test, fail the test. I've heard that lament given too many times from students who've been critiquing computerized homework, and they say, hey, I got every one of these problems right when I was doing it in the computer. But when I took the test, I couldn't put all the pieces together, And that's why it is absolutely critical you write down solutions. You write down these steps, show your work, so that whether I read it or Larita reads it, we see what you did. If you don't, you run the danger. 100% and every one of those problems, the equations, and I hit the test and couldn't do squat. Nothing worked. Now, the homework I gave last night is the first time I've asked you to do something, and I'm hoping, in terms of bringing it back to me so I can look at it, I'm hoping I'm going to be pleased. I know you're hoping too. And I think as I reflected on that, thinking about what we did yesterday in the rain, when I wasn't messing with the camera, trying to make sure the lighting was okay, it occurred to me, that's not an idea that's so bad. Maybe every once in a while, have you turn in an assignment just to see if you can do it. Thank you. I got the approval. Okay, so that's something I think we need to do a little bit more of to make sure that I'm comfortable with what you're doing. I think there has to be some balance between the two. And I'm going to try to make a better effort at that. Some of the problems get pretty messy. Sandra, before we get to the messy problem.
Don't we do that every week for the quiz?
No. Sandra asked, can we do a homework assignment every week for the quiz? No, I'd like to do something with a homework you turn in without making it part of the quiz, so I can get feedback. But I think there needs to be a time pressure with a quiz. The intent there is that there's some time pressure and you are on your own. When you do homework like that, you can sit around, you can talk about it, you can get help, understand it, and to that extent does not reflect what happens on a quiz. Where in a quiz, I'm trying to, in some small way, replicate some of the stress you have in a test. So doing that at least once a week, when you get to a test, you learn to handle the anxiety, some of the stress. And it doesn't do it as well as I'd like, but I'm not willing to do a quiz every day. Now, Sarah does a much more intense effort at quizzes than I do, and she's comfortable with that. My particular approach, a few quizzes, but not enough that I'm probably establishing that environment that helps in your test. So, at any rate, any other comment there? Okay, now back to a messier problem. This is in the top of 248. And you really have to love a 248. 2 to the first, 2 to the second, 2 to the third. So we have this problem in the top of 248. Now, you're going to get caught here, so let me write this one on the board. I know the solution is there, but I want to look at this problem. Okay, that'll sit there. Let me write this out. That minus sign you've got to be careful of, and that's my concern. We have y minus, then a 2y plus 9. Then I have a 6. The 6 is a lot more innocent than that negative sign. A 6 times y minus 2, and a minus 8y. And I'm going to come back to Michael's comment. This should be rigged. When I get done, I should have an x on the left side. One comment. Sometimes you get a negative x on the left side. I could put it on the right side and make it a positive x. Did I miss something in writing this? Well, not okay. You say there's a y versus an x. Finally. Okay. I started to say y. You said y. Why? Whether you have an x or a y or a z is immaterial. My point is you get a variable by itself. So thank you, Marisol. And the key here is what happens if you get negative y on the left side. Then you can multiply both sides by negative 1. You always have a choice to put the x on the left or the y on the left or right. Typically, the left side. Are we ready? What am I going to do, Isaac, with that minus sign? Treat it as a what? A 1. Yes. Now, that's a little bit easier to see than I'm multiplying through by a negative 1. And in fact, you might say, well, wait a minute, that's really plus a negative 1 times 2y plus 9. Or you could have just said, hey, I don't need to play those games. I know immediately this is y minus 2y minus 9. Your choice. Now, if you know that the minus sign simply goes through and changes each of these, then go here. If you need to rewrite this with a minus 1 in front, with a plus sign there, go to it. Okay. Here I didn't change the minus to a plus. Those are all variations. How would I do the problem? There, Michael.
So when we see a problem like this, we simplify?
Yes, you simplify and hope that all that's going to happen here is addition and subtraction. That's your hope. Now on the right side, 6y minus 12 minus 8y. Now I'm sort of doing the left side then the right side more or less simultaneously. What's this going to be in the right side? Give me the final answer here on the right side. Negative 2y minus 12. Okay, now down here, what do I have when I simplify? Minus y minus 9 equals negative 2y minus 12. We've got more minus signs than you may want. Hint, one thing is multiply everything through by minus 1, both sides. Did I miss something here? Michael?
Yeah, what happened to the minus 2y that you had up on the left side?
Well, I had a y and a negative 2y, correct?
Okay.
Doesn't that become negative y?
Okay.
This is Isaac's 1. Now, we want y's on the left, the variable on the left for Marisol. And so I'm going to add what to both sides? 2y. So if I add 2y to both sides, I could write the 2y underneath each part. You might prefer that. So what do I get in the left side now? Okay, Marisol, that was not an appropriate reaction. I have a negative y and a positive 2y. Isn't that y? Thank you. So I have y minus 9 there. What do I have on the right side left? A 0 plus negative 12, which is just negative 12. Well, I don't like that negative 9 on the left side. So I'll add 9 to both sides. Training wheels intact. Y now is equal to negative 3. Is that the way I would have done the problem? No.
How did you get the negative y?
Back to here. I have 1y minus 2y. Wouldn't that be just negative 1y?
Okay.
Back to the negative 1 there. Keep forgetting Isaac's 1. We okay now, Kim? Kim, are we okay now?
Yeah.
Okay. Now what would I have done once I reached this point? I would have added 2y in my head, put down a y on the left side, I would have added 9 in my head, and then immediately gone here. Again, that's what you do once you're trying to build up some speed. This is not a bad idea to carry through here. Let's leave that on the board. Okay, having fun. Michael. Is there any time you need to build up speed in these? Yeah, today. This isn't something we look to a month from now or 6 months from now. It is, okay, get through these, do 100 problems, get the speed up, get on, yeah. You get in the car, you want to drive on the freeway tomorrow. That's where we are. You're in the car, you're going through this process, and you want to be able to be out on the road. It's the way you get at, if you were in junior high, you have patience to do anything you want long enough to make it happen. Later on, you want immediate results. So if you take up the piano, you want to sound like somebody that's been playing it their whole life. Okay? And it doesn't happen that fast. You pick up a guitar, and you may want to sound like Jimi Hendrix tomorrow. It's just not going to happen. So you have to pay your dues. But that's where you want to be anyway. There's some application problems in terms of these exercises, and I'm not going to emphasize those very much. I'm going for just practice and speed. So on page 250, you can anticipate getting problems through 38. I'm going to combine two sections. I'll have that up by about 12:30. I can't get it up and showing yet, but I'll try. I may be able, if I can get the computer to work quickly before I go to the 11:10 class. So there will be problems for two sections due tomorrow, 4.1 and 4.2. So I'll change the, what? On the computer. Okay, Ernie, I'm out of time.